All right, so let's look into an anti-aliasing filter that guarantees no aliasing. So just as a review from the last video, we have a low-pass filter you can make with an RC circuit, the input voltage on the left, output voltage on the right here. The corner frequency is set by the R and C values. So this is an equation there. And then the gain as a function of frequency is given here if you know the corner frequency. So generally you're choosing the order. This would be a first order low-pass filter. And if you ran them in series, you increase the order. So if you ran the output of one into the input of the other, now it's a second order, and so forth. And the goal is to eliminate signals that would be aliased with this low-pass filter. So again, this is the most common approach that's not quite perfect. This one we set the corner frequency, FC, and treat that as FM, the maximum frequency in our signal. It's not really FM because, especially with a first order filter like this, at 13 hertz there's still some signal content. You have to go a ways beyond FC before it gets to be very close to zero. But this is a very common approach and it works fine for many cases. If we have a corner frequency at 12 hertz and we sample faster than 24 hertz, it does allow some aliasing, but it rolls off pretty fast. And again, just to look at the frequency response of that filter, the first order filter here, so if this was our 12 hertz corner frequency, up here you can see we're down in the small gains, but it's not close to zero. So if this is a requirement that you absolutely cannot have any aliasing, you're sending a satellite into space and no one's going to be able to check the data, so you'd have to guarantee no aliasing. We have one approach that works with analog to digital converters. If you don't digitize it, you can't do this because these don't really go to zero ever, they just get smaller and smaller. So, but for an analog to digital converter, at some point small gets rounded off to zero. So we can take advantage of that fact. So if we can make the signal small enough that it can't be measured by the analog to digital converter, then it's zero for practical purposes. So again, this is one way to think about an analog to digital converter. We've got analog voltage on the left. We've got the digitized on the right. So this is an integer. So any voltage in this range is going to come into 1, and this range will hit 2 and 3, and so forth. And so if we can make the voltage this small, it will round itself off to 0. So somewhere in this range, so taking the biggest voltage possible and applying a gain that makes it this size, we will get 0 to the resolution of the analog to digital converter. So this depends on the number of bits. The more bits, the smaller you have to make it because the finer the resolution. So with n bits, the range is divided into 2 to the n steps because we can count from 0 to 2 to the n minus 1. So if we reduce the signal by this factor, 1 over 2 to the n, where again n is the number of bits of the analog to digital converter, it will be 0, even if we started with the maximum voltage here. So that gives us the concept of dynamic range. So dynamic range, dr, the book doesn't really give it a symbol, so I'm calling it that. In decibels is just this gain, 1 over 2 to the n is the factor that we're looking for. So 20 log 2 to the n in decibels is the dynamic range. And so if we attenuate it by the dynamic range, a gain of negative dr, this will be a positive number, but 1 over 2 to the n, it just flips the sign. So we need to have a gain of negative the dynamic range, and then we can guarantee that the voltage we'll measure is 0. So what we're looking at is, rather than having the FM here, FM is going to be out here somewhere, wherever this is negative dr. So when we get it small enough, then it's 0. So we find where the frequency is that our filter design goes through the dynamic range, and that is our new maximum frequency in the signal, because these signals come through, but at some point they're small enough that they're just counted as 0. So it depends on the filters. You can see here, this is the roll-off slope or the attenuation rate. And for a first order, it's -6 decibels per octave, second order -12, and nth order, lowercase n, n for the order, -6 times n. It's really confusing because we have capital N for the bits, and we're going to have n for octaves. The book uses n for everything, and so I'm sticking with that, but trying to point out where it's confusing. So here's an example. We have a system, sensor, anti-aliasing filter going into an analog to digital converter, and we want to, if we're given the order of the filter and the corner frequency of the filter and the number of bits of the analog to digital converter, what is FM? What's the highest frequency that will get through that filter to the resolution of the analog to digital converter? So the question, if we have a second order filter with a corner frequency of 1000 Hertz and an 8-bit analog to digital converter, what is FM? So in our simple filter design, we would say FM is 1000. So remember that when we come up with the answer. And this is an 8-bit A to D. So the first step is to find the dynamic range of the analog to digital converter. So with an 8-bit analog to digital converter, it's 20 times log 2 to the n, where n is 8, and we get 48 decibels. So when we are down at 48 decibels, so down here, that's the frequency where we can't see any signal. So it's off the scale for our second order filter, so little n of 2 crosses 48 down here somewhere. And so we can use the roll-off, just approximate this as a straight line, 12 decibels per octave, and find out the number of octaves to get to 48 decibels. So that's what we're going to do next. It gets a little confusing, so you'll have to think it through very carefully. And the equations are simple, so I'm sure you can at least follow the math. So again, we find the dynamic range based on the number of bits of the analog to digital converter, 48.16 decibels. And then we need to find the number of octaves where our filter has gone down 48.16 decibels. So with a second order filter, it rolls off at 12 decibels per octave. That's the attenuation rate. The number of octaves is 48 decibels divided by 12 decibels per octave. So you can match the units here, and we get 4 octaves. So 4 octaves past the corner frequency is where we can't measure any signal anymore, the frequency where we can't measure that. So that corner frequency is 1000 times 2 to the number of octaves, and that gives us 16 kilohertz. So for this one, to the accuracy of our 8-bit analog to digital converter, we have to go 16 times the corner frequency of 1000, so we get 16 kilohertz. So we would have to sample then at least 32,000, double this, in order to ensure no aliasing in our signal. So again, we are trying to multiply, we're trying to make our filter have a gain that takes any voltage and puts it down into this range, so it comes out as 0. And so with a corner frequency given, at some point the roll-off will go through our dynamic range. And so it's the frequency where the roll-off goes through the dynamic range that gives us FM of the signal. All right, so that's all we're going to do on filters this semester. Hopefully that will take you to a good place in your future career, and good luck with the homework.